In the mid-20th century, the field of aerospace engineering had a single overriding metric: absolute maximum velocity. In October 1947, Chuck Yeager piloted the rocket-powered Bell X-1 past Mach 1.06, shattering the sound barrier and launching a global race for supersonic dominance. This effort produced legendary aircraft like the Mach 3.3 SR-71 Blackbird, pushing the physical limits of flight further with every iteration. But if you look closely at the record books today, you'll notice an engineering anomaly. The absolute fastest planes in history are all over 50 years old. Put a modern, cutting-edge fifth-generation fighter like the F-22 or F-35 on a runway next to those mid-century jets, and the modern aircraft will lose a pure drag race every time. This animated graph tracks top aircraft speeds. You can see the line surge upward during the 1960s as engineers tested aerodynamic limits. But then the trajectory drops off. By the 2000s, it levels out completely. We effectively hit the brakes on top speed. We didn't lose the ability to build faster engines. We realized that in aerospace, velocity exacts an astronomical toll. We encountered engineering trade-offs that forced a complete pivot in aircraft design. Push an aircraft past Mach 2.5 and you enter the thermal thicket. At these velocities, air friction generates blistering heat and immense pressure, threatening to melt the metal. To survive this environment, American engineers designing the SR-71 Blackbird forged the airframe out of titanium. This scorecard breaks down the reality of that decision. The hurdle was thermal friction, the input was a titanium airframe, and the outcome was a jet cruising comfortably past Mach 3. The trade-off was a difficult supply chain, requiring bespoke manufacturing tools just to handle the metal. The Soviet Union faced the same thermal problem when developing the MiG-25 Foxpat. Lacking the infrastructure to source and mill massive amounts of titanium, Soviet engineers opted for heavy, heat-resistant stainless steel. It solved the melting problem, but added massive weight to the airframe. On paper, Western intelligence saw the MiG-25 and believed it could sustain speeds of Mach 3.2. But that spec sheet number hid a fatal flaw. If a pilot pushed those conventional jet turbines to Mach 3.2, the engines would overspeed and tear themselves apart, requiring complete replacement upon landing. Surviving the thermal thicket presented a severe binary choice. You either spend immense national wealth securing rare metals, or you push cheap metals to the point of destroying your own engines on a one-way run. To push past Mach 3.2, engineers had to completely abandon traditional air-breathing jet turbines. The North American X-15 reached Mach 6.72 by strapping a rocket engine to a cockpit, but it required a B-52 mothership and its fuel burned out in minutes. The next evolution was the scramjet, powering the NASA X-43 to Mach 9.6. However, hitting Mach 9.6 required another massive sacrifice, removing the human pilot entirely. For tactical combat, engineers tried a middle ground, the variable sweep swing wing of the F-14 Tomcat, which allowed high-speed interception paired with low-speed carrier landings. The trade-off was immense mechanical weight and maintenance. The complex wing box mechanics created critical points of failure requiring specialized maintenance. Swing wings were an ingenious workaround, yet the sheer maintenance burden proved that adding heavy mechanical complexity to solve the speed problem was a dead end for a sustainable fleet. The era of the high-speed Sky Demon ended because the engineering return on investment simply inverted. Experimental craft like the X-15 and X-43 sit far to the right of the cost-utility chart, incurring astronomical costs for load. To solve the speed problem was ultimately a dead end for a sustainable global fleet. We have to look at the return on investment in engineering. For every extra knot of speed gained, the cost of specialized parts, man-hours for repairs, and logistical chains grew exponentially. This brings us to the core of the issue, the quadrant of strategic combat utility. If you plot historical aircraft by their daily combat effectiveness against their total life cycle cost, a clear trend emerges. The experimental craft, the record breakers, sit far to the right, incurring astronomical costs for minimal daily utility. The Cold War interceptors, while legendary, still demand massive specialized maintenance budgets that bleed resources away from other tactical needs. But look at the modern landscape. Today's fifth-generation fighters, the F-22, the F-35, the Rafale, they cluster in the center left of that chart. They aren't trying to break the sound barrier by a wider margin. They are designed to be sustainable multi-role platforms. We stopped chasing the speed demon title because we realized that air superiority isn't about being the fastest in a straight line. It's about being the most capable in a contested environment. During the Cold War, militaries had to physically outrun analog radar and early surface-to-air missiles. That threat justified the financial cost for raw speed. Today, strategists know trying to outrun a network defense system is a losing bet. Advanced avionics, precision weapons, and near invisibility yield better survival rates. A fifth-generation fighter like the F-22 prioritizes stealth technology and internal weapon bays over top-end velocity. You don't need to fly at Mach 3 if the enemy doesn't know you were there. The SR-71 and X-15 records stand today because modern aerospace prioritizes stealth and range over raw speed. Engineering success shifted from maximizing velocity to finding the point where capability meets sustainable reality.